Good morning. My name is Dr.S.ARUNKUMAR, Assistant Professor of Mechanical Engineering, SNS College of Technology, Coimbatore. So in this video series, I am going to discuss about some topics on thermal engineering. The topic is calorific value of fuels and the combustions. So we know that what is calorific value. So calorific value is nothing but it is the amount of heat evolved by complete combustion of 1 kilogram of fuel. It is called calorific value. So in this presentation I am going to discuss like this agenda, calorific values of fuels and combustions, calorific value and combustion process. There are three stages, reaction stages, combustion products and the complete and versus the incomplete combustions. Coming to design thinking approach, in this lecture series we are going to discuss about the empathize stage as well as the prototype stage and some of the real world applications like power generation, automotive engineering and industrial heating. So calorific value represents the total energy released when a fuel undergoes the complete combustion with the oxygen under the standard conditions. So the measured in kilojoules per kilogram, it is the unit of calorific value of the fuels or megajoules per kilogram. This fundamental property determines the fuel selection for engineering applications. So there are two types. One is higher calorific value and another one is lower calorific value. The higher calorific value includes latent heat of vapor condensation, while the lower calorific value includes, it represents the practical available energies. So this is the types of higher calorific values. We already discussed higher calorific value as well as lower calorific values. So the higher calorific value HCV, also termed gross calorific value, which measures total heat released when combustion products cool to standard temperatures and water vapor condenses to the liquid state. Lower calorific value, the net calorific value excludes the condensation heat, representing the actual usable energy in most practical systems where exhaust gases remain above water's dew point. The lower calorific value is calculated by using these formula, like is LCV is equal to higher calorific value minus M into 2257 kilojoule per kilograms. So where M, it represents the mass of the water formed per kilogram of fuel combust. The difference typically ranges from the 5 to 10% depending upon the hydrogen contents. So this is the sum of examples of comparative fuel calorific values. The comparison is plotted in the graph like wood, coal, diesel, petrol, natural gas and the hydrogens. So compare then all the fuels. The hydrogen has the high calorific values. So the combustion process, it represents the rapid exothermic oxidation reactions between the fuels and the oxygen, that releasing the energy as heat and light. For complete combustion, sufficient oxygen supply is critical. The fuel plus oxygen, it reactants mix at the molecular level, and ignition, activation, energy overcomes the molecular bonds, and reaction, rapid oxidation release energy. Products, the output from the combustion is CO2 and H2O and heat energies. So this is the comparison between the complete combustion and the incomplete combustions. The products like carbon dioxide, water vapor and maximum heat release, these are the output products. And requirements for the combustions are adequate oxygen supply, theoretical air fuel ratio or excess air, and characteristics are blue flame, minimal smoke, highest efficiency. For example, CH4 plus 2 oxygen O2, it gives the carbon dioxide plus 2 molecules of water, that means 2 H2O plus energy. So coming to the design thinking approach, the first stages of design thinking is empathize stage. So understanding the user's needs, engineers must empathize with the end users facing the fuel efficiency challenges. So industrial operators struggles with the rising the energy cost, while the environmental regulations demand the cleaner combustions. Through the interviews and site observations, we identify the pain points, inconsistent fuel quality, incomplete combustion losses and the maintenance burdens. So these are the problems. The problem identification is the manufacturing facility reports 15% of fuel wastage due to the incomplete combustion in their boiler system. Workers express concerns about the safety risk from CO production, carbon monoxide production. By empathizing with the operators and understanding their daily challenges, engineers frame the problems, optimizing the air-fuel ratio while ensuring the safe and efficient operation within the budget constraints. So the last stages of design thinking is a prototype stage. The prototype stage is nothing but it is the solution development of any problem. Based on the empathy insights, engineers prototype on automated air-fuel ratio control systems. The prototype includes oxygen sensors, programmable logic controllers, and real-time monitoring displays. Testing approach, small-scale implementation on one boiler unit before facility-wide deployment, and iterative refinement. Operator feedback shapes interface the design and the control algorithms like initial prototype design and component selections, laboratory testing under controlled conditions, and pilot installation with the continuous monitoring, refinement based on the performance data and the user feedback. Some of the real-world applications are power generation, automotive engineering, industrial heating. Gas turbines and the coal-fired plants utilize the high calorific value fuels for electricity productions. The modern plants achieves the 40 to 60% of thermal efficiency through the combined cycle systems. Automotive engineering, the internal combustion engines rely on precise fuel-air mixture ratios for optimal performance. Petrol and diesel calorific values determines the engine design, compression ratio, as well as fluid injection systems. So the efficiency based improvement is based on the reduced the fuel consumption as well as emissions. Industrial heating, manufacturing processes requiring the consistent heat supply for operations like metalworking, chemical processing, and the steam generation. The boiler system must balance the fuel cost as well as efficiency requirement and the environmental compliance through the optimized combustion control. So some of the key takeaways from this lecture series, calorific value fundamentals, we already discussed. There are two types of calorific values. One is higher calorific value, another one is lower calorific value, and combustion optimization and design thinking applications in the particular topic. So these are some of the references of this lecture PPT. Thank you for watching.